Hi there. So the subject of this lecture is scope and lifetime. Okay, so what I want to do is discuss this concept. You've heard of this term before, scope. So you know that this idea, there's a variable x, and like sometimes you can use x and sometimes you can't. It's like, what are those rules? Those are scope rules. All right, and there's a common rules that you're probably familiar with. So here is an example in what pick your language, C, Java. We have a variable z that's being declared inside of the if statement, and the standard thing is that it's going to be scoped within those curly brackets, and those curly brackets sort of determine where the variable is meaningful, where that declaration takes place. So one thing is when we informally speak about programs, we often just talk about the x or y. But if you look at the text of this program, the variables occur multiple times, and so if we're going to talk about the structure of the program itself, we need to distinguish these various occurrences of the variable name. So there's some terminology that we need to have in order to talk about the different ways that the variable is used in the program. Okay, so we talk about we don't just say, oh, there's the variable x. We say, okay, there's a particular occurrence of the variable x. X may occur in many different contexts and in many different meanings. So we say that a variable occurrence is free when there's no matching binding. Okay, so here, if you just look at this expression, we have y equals 5 times x. So in C or Java, y and x there, they make no sense. They have no particular meaning. We don't know how they were declared. And so we say that these things are free. Free things, of course, they're allowed to be anything, or said differently, they're meaningless. So in order to give them meaning, we have to declare those variables. So in Java and C, we declare them with the same syntax. It's like this. We've declared variable y. This is a binding or occurrence or a declaration, right? So we have free occurrences and binding occurrences. And what happens is when we take a free occurrence and we put it in the context of a binding, then it becomes bound, right? So it sounds so sad. It's like you were free and now you're bound. But actually in a programming language, this is a good thing, because another way of saying it is you were meaningless and now you have meaning. Here you can see there's if you look at this line here in isolation, x gets 6, x is free. But in the context of this declaration, then the occurrence is bound. So what we expect in a programming language is that all of the occurrences should be either a declaration or they should be bound. So we don't want any free occurrences, because if we have free occurrences, we don't know what the program should do. All right, so what do IDEs do with free occurrences? They typically sort of underline them and say, I'm sorry, things are bad here. You need to provide a declaration of this variable. It's worth pointing out that this notion of scope and this notion of declaration, it applies to all sorts of things, not just variables. So it also applies to function parameters, to class names, and all sorts of other stuff. So you need to declare a class before you can refer to the class in Java, for example. So older languages were designed to be compiled in a single pass. What that meant is they wanted to, because it used to be things were relatively expensive, so going through files multiple times was too costly. So they wanted to design languages so that each individual file could be gone through exactly once. So this led to languages like C requiring forward declarations. So what is a forward declaration? In the case that I have two functions that are mutually recursive, so here I have G and F, and note that G calls F and F calls G. Well, if you're just parsing the file from beginning to end, when you look at this declaration of G, if you looked at it in isolation, you'd say, well, F, what is F? If F did not refer to G, well, we could just put F first and we'd be fine. But in this case, they refer to each other, and so there's no way to order them so that we don't have one, referring to something meaningless. So the solution is to put these what are called forward declarations or prototypes into the language. And if you look at this line, what it's saying is that there will be some definition of the function f, and it will take an integer and return a character. But I'm not going to tell you right now what it is. But trust me, it will be defined. And this is sufficient to get the type system to pass the definition of G, and therefore when f actually does appear, everything is fine because now we have declarations of both f and g and we can compile the function. Another phenomenon that we have in programming languages is shadowing. So this is when we have the same variable being used multiple times in the same context, or the same name being used multiple times in the same context. Shadowing is illegal in Java, so in most contexts. Okay, so actually, I speak a little too cavalierly. Shadowing of local variables is illegal. So if I have a local variable here, x, I cannot declare another local variable x. The compiler will reject the program. Okay, so but for other things, Java is fairly more liberal. So, for example, if it's a field can be shadowed by a local variable. So here the local variable x is covering the field x. That's just fine, and Java understands what it means, and it sort of does the right thing. In fact, this is used all the time in Java. C is less strict than Java. It allows shadowing even of local variables. So here x is declared that I'm declaring another scope with y, and finally a third scope with a new declaration of x. And this is just fine in C. This is not allowed in Java, but it is allowed in C. And Scala is in fact more like C in this respect than Java. So Scala allows shadowing of local variables, even though such a program would be rejected in Java. And it's worth noting that this is what's happening when you're in the read-eval print loop of Scala. So what you're doing is constantly shadowing old declarations. So let's suppose I declare a variable a value x, and I define a function here which will return x plus the parameter a. So obviously here x is 1, so if I call f on 10, I get 11. If I then reassign x, what's going to happen? Well, note that actually this is not actually changing the old value of x. What I'm doing is creating a new value of x. And so how do I know that? Because, well, this is a val. It's not mutable. So this is a new declaration which shadows the old declaration. So if I just try to access x then, of course, I'm going to get 2. The way that I can tell that this is really shadowing is by going back and trying to look at f. Because note that f refers to the old declaration. That old declaration is still there. And so if I call f, it still has the same behavior. It's not using the new x, it's using the old x. So that's why it's called shadowing. It's like the old thing is still there, it's just you can't see it. It's hidden. That's shadowing. So This behavior of the REPL, what happens in the REPL is every time you declare a new thing, you're essentially opening a new scope. That's the right way to think about it. And that new scope then has the new variable. So you're continuously opening new scopes. So one of the interesting things, and this is the last thing I'll say about scope for now, we'll come back to it in a later lecture, but one of the interesting things about scope is that it is what do you do in a case like this, where I have a declaration of a variable and it has an initializer, and the initializer actually refers to the same name as the variable that's being declared. What does that mean? And there are many possible meanings to that. So one possible meaning is, oh, maybe over here I'm in a different scope, and this scope refers to the outer X. That's a perfectly sensible definition, but it's not what Java or C or any language I know does. The languages that are familiar these days, what they'll do is they'll say, okay, well, you've declared X, and so this X obviously refers to this declaration, and now we have a problem because X here cannot be initialized because I'm using it to initialize X. So we get warnings in this case from C, errors from Java if you try to do this. All right, so that's the concept of scope. Scope is a static notion. It's a concept that has to do with reading a program and knowing how to interpret the names. Like when I see a name, which declaration does it refer to? The dynamic correspondent of that is lifetime. So the lifetime of an area of memory is when you declare it to when it is deallocated. So we allocate the space, then we deallocate the space. There's a bunch of stuff in the textbook on programming languages by Mitchell, in particular chapter 7, and you should have also seen a similar stuff in your systems class. All right, so activation records, as I mentioned in a previous lecture, are the place where we put local variables. They're also known as stack frames, and they're almost always done in a stack protocol because we call things in a LIFO order, as I said earlier in a previous lecture. So we end up with sort of 3 separate storage options which are typical. So there's usually different classes of storage, and these are the canonical ones that are sort of used in languages like C and Java. So we have global variables or static variables. These are available the entire life of a program. There are activation records, which are used to store local variables and parameters, and those are alive for the life of a function. So that's as long as the function has been called but hasn't yet returned. And then we have heap allocated memory, which is explicitly allocated and often explicitly deallocated as well. So it may be explicitly deallocated or dealt with in some other manner, like reference counting or garbage collection. So what can go right, what can go wrong? Well, you know, if our program's good, we always have the storage when we need it and we don't use too much. But we can also have lifetimes that are too short, meaning that we've released some memory prematurely and we're still accessing it. That means we might read invalid data, we might overwrite some thing that's being now used for another purpose. We can have all sorts of security problems because of this. The other issue is that we might have a lifetime too long, and I claim this is why I have to reboot my phone every so often. Actually, Apple now routinely reboots applications, so it just kicks them out of memory and then causes them to restart. And one of the reasons for that would be to stop memory leaks. So applications that are allocating memory without releasing it. One way, of course, to do a nice way of releasing all the memory in your system is just to reboot it. And that's one way of getting sometimes better performance on your machine if it starts to get sluggish. But it's really a bug of the program. I mean, programs should not carry around or keep memory that they don't need. And so this is typically a problem where we're too late freeing resources or getting rid of things when objects die. All right. So the standard way of sort of keeping track of the stack is using these things called control links. So what a control link does is it points to the previous activation record so that when you return, you can go back to that previous activation record. This is the standard that was used in Intel processors, all of the 32-bit processors. They have abandoned that in the 64-bit processors. The 64-bit processors, instead of keeping links to the previous record, they just keep track of how big the record is, and they subtract that amount from a pointer to indicate how much data there is. So we have this stack of activation records. The great thing about it is it's super fast. Allocating a new record is just a couple of operations, so it takes no time. Deallocation is also just a couple of operations. We're just subtracting a stack pointer. And with heap allocation, it's much more expensive. We have to go find an appropriate thing of the appropriate size. That's typically going through a linked list of the free memory elements until we find one that fits, and doing other stuff to sort of make sure that we're not taking too big a chunk, etc. So heap allocation is relatively expensive, both for allocation and deallocation. Stack allocation is awesome. So people love it, and it's used a lot. It's the stack discipline says that when we call a function, we're going to allocate data or space for that function. If we call another function, g, we'll allocate space for that function. And of course, functions return in the reverse order that they were called, so we'll always return g before we return from f. And so that is why we can use a stack for these things. All right, if we have a bunch of threads, what is a thread actually? A thread is really a call stack and a code pointer. So each thread typically has its own stack to keep track of its independent state, as well as a code pointer saying what it's executing. Whereas threads have separate stacks, they usually share the heap. So the heap is a big chunk of memory that we can go and allocate and deallocate things in. So we have all sorts of patterns we can do there. We can allocate some number of bytes, allocate more bytes, and then we can keep them and deallocate them in the same order that we allocated them. We can do them in stack order, blah, 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 any order. It's irrelevant of the order that we allocated them. So the allocation and deallocation are completely independent. Again, this is great in terms of freedom, but the cost is it's more expensive to implement. So, sort of common problems we get here are that we may keep things around too long, so that's a memory leak, and that can happen in these languages like Java, Scala, C#, etc. But for the languages with manual memory management, we can actually have real problems with things that where we maintain references to things that have already been deallocated. So we've seen some of this already in our early homeworks and in terms of the undefined behaviors of C. And I'll show you a few more examples here. So we might have dangling pointers into an old activation record, dangling pointers into freed memory, or we might free memory multiple times, which can get us into trouble. So here's just a very simple example. And what I want to show you here is that dealing with memory problems is tricky, but there are some tools which can help us. So I'm just going to show you one tool. I'm going to show you how it works, or the kind of output you get from it, and just to give you some feel for what you can do in terms of dealing with these kind of memory lifetime issues. All right. So here's a function f. What does it do? It has a local variable y and a parameter x, and it returns the address of its local variable y. The main program here takes the address that it's given by the function, and it attempts to dereference that address and print out the result. So in older versions of GCC, this actually gave us a warning, and it worked just fine. In current versions of GCC, this will actually give you a core dump, because current versions of GCC will actually return the address 0 here rather than returning the address of the local variable. The reason they can get away with that is that this is an undefined program. So we have undefined behavior in GCC, and so the compiler can do what it bloody likes. But in any case, this is, in some versions of the language, a dangling pointer, which can cause some trouble. You can find these things by doing some analysis. So one of the tools that's available is called valgrind. Valgrind is, you can find it on the internet. I'm not actually going to run it live because it's not configured correctly on my current machine. So what it does though is it will take a executable file and run it and try and find the kind of problems that are there. And it's actually quite good. So it'll find lots of issues if they are there. So here you can see there's a use of an uninitialized value, and it tells you exactly what's happening here. So this is a version that's been fixed where it's not dangling. And in fact, valgrind says, yay, everything is super fine. So there's super fine, no uninitialized memory being accessed. This program does have one other problem though. It has a leak. And you know, whether you consider this a problem or not, it's usually when you allocate something, you're supposed to free it. And obviously in this case, it's a short-lived program, so it's going to be freed when the program exits. But valgrind points out that this is a problem in the sense that you have not actually freed that memory. So what do we need to do to make it accurate? We actually need to free it. This is a real common sort of C error here where I free it before I use it as opposed to afterwards. So this will be found by a program like valgrind. It can actually find these errors and report on them to you. So if you're ever forced to do a lot of C programming and you're worried about these kind of these kind of memory violations, using an analysis tool like that can really help.